So yesterday we investigated or reminded ourselves of the exponential functions that we studied last semester, and we discovered this brand new one, special exponential function called e. Today we're going to remind ourselves of the exponential function, the logarithmic functions that we studied last semester, because we're going to look at the derivative of logarithms and stuff like that. So first we better remind ourselves of the different rules for logarithms and how it all works. So this is just a quick review of logarithms from MCV4U. So when we have, you should have the worksheet in front of you with these notes to make this a little bit faster, or at least the blanks of the notes. So we should be able to go through this relatively quickly. Remember, when you're putting things in logarithmic form, here's an exponential form. We're going to write log, and it is log 5, or log 25, excuse me. And the base goes here, and then the answer is an exponent of 2. So here's the base of the exponent, so the base goes right here. The answer is 25, and the exponent is what a log is, because remember, logs are exponents. And remind yourselves, what this says is, what exponent do you put on 5 to get 25? And the answer, of course, is 2. So in this case, we're asking, what exponent do you put on 4 to get 64? So it's log 64, base 4. What exponent do you put on 64 to get 4? Well, it's obviously 3. So that's putting it in logarithmic form. We can go the other way. If I give you a logarithm, this is asking, what exponent do you put on 9 to get 81? And the answer is 2. So that means it's 9 is the base, 2 is the exponent, and the answer is 81. And remember, if you don't see a base, you understand that it's base 10. So that's 10 to the power of 2 is 100. So little reminders from last semester. Then a couple of these rules pop out here when we evaluate these next ones. So the first one, 3a, says, what exponent do you put on 6 to get 6? So the base is 6, the exponent is 6. What exponent do you put on 6 to get 6? Well, obviously that's 1. Because 6 to the 1 equals 6. B says, what exponent do you put on 6 to get 1? So same idea, 6x equals 1. So we should remember that 6 to the power 0 is going to get you 1. So log 1, regardless of the base actually, is going to be 0. Next, this is asking, what exponent do you put on a to get a to the x? Well, that one is just x. This is one of the observations. What exponent do you put on a to get this? Well, it's right there. It's x. So a to what equals a to the x? Well, obviously, it's x. And similarly, the opposite of this, you take a, you raise it to some exponent, and you get x. And now take that exponent and put it on a, and guess what? You're going to get x. Again, convert this. This is an exponent, an exponent. So it's log. The exponent of this, or the base of this exponent, is a. The answer you don't know, but it equals the exponent log a to the x. So obviously the unknown is just x. So those are a couple of the characteristics and features that we need to remind ourselves when we are doing logarithms, because we're going to end up differentiating logarithms. One other thing I wanted to remind us of is the sketches of this. So let's remember this. This isn't a logarithm. This is an exponential function. So it's y equals something to the power of x. We usually just graph 2 to the power of x, but you could do 3 to the power of x, 4 to the power of x, whatever. They all kind of look like this. They all go through 1. because regardless, b to the power of 0 is going to be 1, so it doesn't matter what the base is. If you put it to the power of 0, it's going to be 1. And so all of these sort of look like this: y equals b to the power of x. And if you recall, when we look at the inverse of this function, remember the inverse is when you flip the x's and y's. So instead of y equals b to the power of x, this is x equals b to the power of y. What's it going to look like? Well, when the x's and the y's switch, we used to have a point right here at 0, 1. Now it'll become 1, 0. And then all of these numbers here will go off like this. These ones will come down like this. These negatives will become these negatives. The positives become positives. We have this inverse. Now, the inverse is x equals b to the power of y, but I don't like writing it like that. I'd rather write it in logarithmic form because y equals log b to the x, or sorry, log x to the b. All of this is a fancy way of saying that logs are inverses of exponential functions. And this was something we discovered last semester as well. So, if we combine what we learned yesterday with what we were reminded of today, we can consider not just any old exponential function, but this brand new exponential function, the e to the x, the one that we just discovered yesterday. So y equals e to the x looks like all sorts of other exponential functions. It goes through 1, because even e, 2.71 and all that sort of stuff, even e to the power of 0 is 1. It has an inverse. This special one, just like all the other ones, it has an inverse. And if the exponential function is important, a pretty special one, so much so that it gets its own name, if that one is special, then the inverse of it must also be special. So let's consider the inverse of the e function, Euler's constant. So in this case, it's going to look like this. It's going to be y equals log of x base e. This one is a special logarithm. Just like e is a special exponential function, the inverse, the logarithm of e, is a special logarithm. It's called the natural logarithm. That's what it's called in English. In Latin, though, it's called Logarithms Naturalis. So since this concept was discovered in Latin, we use their notation. So L and N, the logarithmic naturalis, and we have a new name for this special logarithm, and we call it ln. It's pronounced ln, L-O-N, but it's not L-O-N, it's just L-N. And so ln of x is just a special name for this special logarithmic function with a base of e. So we're going to use ln quite a bit, but remember that it's just a regular, it's just the same, has all the same properties as regular logarithm. The only difference is instead of like log base 2 or log base 3 or whatever, it's log base e. And since it's so special, it gets its own name called ln. But all the same properties apply that we studied or reviewed in the first page. So if we had the ln of all these, all the same rules would apply. It's just this one gets its own special name.